All right, you had Lewis structures in general in your review section. We're going to look at one part of drawing Lewis structures that we did not look at last year, and that is going to be what we call formal charge. First, we're going to start off with is just the definition. All right, formal charge is just a charge an atom would have if all your atoms in the molecules have the same electronegativity, meaning if they are all shared nice and equally, this is the approximate charge that they would have. Now we know that not all atoms have the same electronegativity, so they don't all share equally, but this is just one way to kind of keep track of charge. And there are a couple different ways we're going to look at throughout the year. And the overall charge or oxidation state is one, and a formal charge is kind of the other. When we calculate a formal charge, okay, since everything is shared, that means that all unshared electrons are counted towards the atom that they are on. So for instance, if you look to the right here, this oxygen has 2 unshared pairs. So those 4 get counted just for that oxygen. It has 4 around it that are not shared with anything else. When we look at them, these shared pairs, those are shared, and we're going to say whether they're shared equally, so we're going to count them right in half. So a half are counted to one atom, the other half are counted to the other atom that it is bonded to. Then to figure out an actual formal charge for that particular atom, you look at what the valence electron number it would be for that element, and then you subtract these assigned electrons that you just figured out based on shared and unshared pairs, and that is a formal charge. So let's look at the example here on the right that I was talking about. So I said oxygen earlier has 4 unshared pairs. Okay, the 2 on the top here and the 2 on the bottom. Then it shares these 2 with carbon, so you cut it in half, and there are 6 total electrons that are assigned to that oxygen. We know the valence electron number by the group number, and so oxygen is in group 16. It has 6 valence electrons. 6 minus 6, its formal charge is 0. We do the same thing for carbon, the same thing for the other oxygen. And here's another possible structure for carbon dioxide, and we assign the numbers again. This time the oxygen has 7 assigned to it because it has 6 by itself and is sharing 1. So the question becomes, why formal charge? Well, just what you see right here. Based on resonance, there are lots of options for structures. So how do we pick a good structure? Well, you look at the formal charge. And so based on formal charges, you can figure out which one of these 2 is the more preferred or more likely structure. And when you want to figure out and choose this most likely structure, you either want everything to be 0, like you see in this carbon dioxide up here, so all 0 is good, or the most negative number should be on the highest electronegative atom. Because that means then that charge is going to be negative. Well, that atom is the most electronegative, so it wants those electrons. I don't want to have a negative on something that actually would rather not have electrons around it. You can also tend to lean towards structures that are symmetrical. You don't have lopsided charges. So up here, that's a good example of this carbon dioxide, why that's not a very good structure. Because I've got one oxygen that's +1 and one oxygen that's -1. I would much rather have both oxygens have the same charge, in this case 0. You do want to keep in mind that formal charges do not represent actual charges, they just help us pick a good Lewis structure. Let's look at the practice. Okay, the following are 3 possible Lewis structures for the thiocyanate ion, NCS. Determine the formal charges for the atoms in each structure and which structure is preferred. Okay, so we have our 3 possible structures here. You can have a single bond to N and a triple to S, 2 double bonds, or a triple to N and a single to S. So let's figure out then what the best structure is. So go ahead and assign the formal charges to each one, and we'll pick one. Okay, so looking at these, we want to pick the best structure. Well, this first one is too lopsided with a positive 1 and a negative 2, and they're both fairly electronegative, N and S. So it's got to be one of these two here. So when we pick one, we need to figure out which one actually is more electronegative, N or S, and it is a little bit tricky. You would think that S, which is catty-cornered to F on the periodic table, that it would be more electronegative. But in actuality, your N is, and so we're looking at this one here. It also helps that you have two double bonds here, so it's symmetrical, and molecules tend to take these symmetrical avenues. The last thing we're going to look at here is resonance, and we're going to look at resonance in benzene. Okay, we did not talk about these last year. Aromatic compounds, or what we call benzene, is one of them. C6H6, we have these hexagonal rings, and there are two equivalent Lewis structures. Just notice how the double bond just moved. Remember, that is our resonance. Okay. Now, when we look at bond length with these, okay, I want to figure out, just like we looked at for every other resonance structure, about what their actually bond length is. Well, the bond length is actually about 1.5 bonds, because each one around here is a single or a double. So in essence, it's actually about 1.5 bonds. They are an average of the single and double. So you'll often see benzene written in a shorthand notation, which looks like this. This is saying that all of those are actually the same bond length, 1.5. We don't write the hydrogens, and each corner is a carbon. And we'll talk more about these benzene rings at the end of the year when we deal with organic. So let's look at another hydrocarbon, which means carbon and hydrogen. Has 3 double bonds and 3 single bonds. It's called hexatriene. Now, would you expect hexatriene to have multiple resonance structures, just like benzene does? And why or why not? Well, when you look at this, there's a problem with this one. You cannot have multiple resonance structures for this one, because if this bond moves, you're going to end up with only 3 bonds to carbon. 3 bonds to carbon is not good. So this bond, these bonds here, cannot go anywhere. They can't move. So you have to have a double bond on the end to make this structure work. It can't work any other way. So this is a definite no. It cannot have multiple resonance structures. You're going to end up with 3 bonds to carbon on the end. And carbon always forms 4. So 3 bonds to carbon won't work.